Cape Talk, the world of science with Dr. Chris Smith, the naked scientist.
Good morning, Chris.
Hey, good morning
How are
to you.
you?
Yeah, in very good shape, thank you very much. You?
Fantastic, thank you. My grandmother was a diabetic. I had to prick her every single, or she had to prick every single day to check her insulin levels. You have an interesting story regarding diabetic responses.
Yes. So a group of researchers at the University of California, Los Angeles, have taken us a step further towards what scientists dub smart insulin. Now, at the moment, a person who has diabetes either cannot make enough or cannot make any of the hormone insulin. If you're type 1 diabetic, that means you can't make any insulin. And in both cases, people have to keep an eye on their blood sugar levels because insulin controls blood sugar. And if you don't have enough insulin, under certain circumstances, you have to inject it through the skin, and the insulin then goes to your tissues and says, take out the sugar from the blood and store it, which is why blood sugar then comes down. But this is inconvenient for people. And also there's a limit to how quickly you can test blood sugar, inject insulin to keep the sugar level at the level that's healthiest for the body. So what this group led by Zhen Gu and his colleagues have done at UCLA is that they've developed a molecule. You can imagine this as a bit like a giant ball of wool. It's called phenylboronic acid, the molecule they've used to make into a polymer. And this naturally has the right charge on it so that you can add insulin to it and it soaks up the insulin rather like you putting the sponge in the water in the bath and it takes up a load of water. Mm-hmm. So you get this molecule full of insulin. You can then inject this, and when it sees sugar in the blood, the molecule is forced to displace a certain amount of the insulin it has locked away inside it back into the bloodstream. And it displaces the right amount of insulin to make up for that level of blood sugar. So critically, as you have a higher blood sugar, it releases more insulin. As you have a lower blood sugar, it releases less insulin. So there's no danger of this suddenly triggering a hypo.
I see. And it measures that how?
Because
on an ongoing basis?
It's a smart molecule, which means literally the chemical nature of the molecule itself. When glucose binds to it, it changes the charge on the molecule, which then pushes the insulin out. It's analogous to the glucose giving the molecule a squeeze to push the water out of the sponge. And this will be much more convenient for people, but it also means that you could achieve much more rigorous control of blood sugar within tighter bounds and therefore probably have a better health outcome. Now, it's very early days. They've done this only in mice and in pigs with animal equivalents of diabetes, but it was very effective, not just in the short term, but over the long term as well. There are some risks with this because obviously you're putting very large amounts of insulin into the body, albeit locked away in this molecule. So you have to be really sure that some other chemical isn't going to come along and accidentally trigger the release of insulin, which isn't glucose, because if something other than sugar were to release the insulin, it would plummet, your blood sugar would plummet.
Clint, related to diabetes, Clint would like to know why diabetics lose limbs.
The reason for this, and it's usually people who have type 2 diabetes who suffer limb loss, is that whenever the blood sugar level is not correct, and usually when it's too high, this has the effect of accelerating the occlusion or blockage of blood vessels because of arterial disease. So we know that diabetes is a high risk factor for arterial disease. And it's not just the sugar, because people who have diabetes have a metabolic syndrome, which also throws into disarray the blood fat levels, cholesterol and the triglycerides in the blood, both of which have an effect on how fast arteries fur up. And so people who have diabetes are at higher risk. It's not a given. If you control your diabetes really well, then your risk is minimized, but you will have a higher risk if you have diabetes of occluding blood vessels, and because you block up blood vessels, you then are at higher risk of tissues suffering a lack of blood flow, and that can cause necrosis and gangrene. The other thing that diabetes does, and people have to be very careful about, is that it also damages nerves. You can get diabetic neuropathy. And this means that people may not be able to feel properly what's going on in their peripheries, because the areas of the body where the nerves are longest, such as your toes and feet, those nerves are most vulnerable to this neuropathic effect. And if people can't feel that, for instance, their shoes are a bit tight and they're rubbing on their foot, or they've got a stone in their shoe and it's made a hole in their foot, you can then end up with ulcers, and they can become infected, and this can lead to infection, which can lead to limb loss, and also it can get into the bones. You can get a condition called osteomyelitis, which is also quite nasty.
Ellis sent us a question during the week, actually. He got it in very early, asking about solar flares. He says, when a coronal mass ejection occurs, Carrington effect, magnetic energy is expelled into space. Presumably, it travels at the speed of light. And he says maybe this is where his presumption is incorrect. And he says this energy or light heads towards Earth. First thing encountered are satellites that detect energy and warn of danger, or are visual detected giving warning. The problem being, by the time we see the danger, it is on us. How are we able to detect the flares in time to take preventative action? Cheers. Ellis, I hope you're listening, because you're the only one who'll understand the answer.
Hello, Ellis.
Besides Chris.
You're referring to coronal mass ejections, or solar flares, which are the ejections from the surface of the sun of bolts of plasma and charged particles and radioactive particles that come streaming off the surface of the sun. We think they're flung into space because the sun has a magnetic field, and for reasons we are still trying to understand, that magnetic field can become taut and tight and wound up, and it then unleashes this energy by flinging into space some of the plasma and other charged species around the surface of the sun. And this happens periodically, but the sun goes through cycles when it happens more and cycles when it happens less, and it's tied up with what sunspots are. And the Carrington affair is named after the astronomer Richard Carrington. He was a UK astronomer who in the 1800s spotted, quite literally, these marks on the sun that were huge. They were sunspots, and then predicted that this was going to lead to the ejection into space of this enormous surge of material, and that there would then be consequences. Now, where Ellis is slightly off the mark is that the sun is ejecting radiation into space in the form of light, and light travels at the speed of light, so it takes 8 minutes for the light to get from the sun to the Earth. But the physical material ejected from the surface of the sun, the particles, radioactive particles, other cosmic matter, that runs at about 1 million miles an hour, so 1.5 to 2 kilometres, 1 million kilometres per hour. And as a result, there will be a significant lag between the time that we see these things forming and the sun's magnetic field changing and other configurations that we can see on the surface of the sun building up. We can see this happening, and then that material being ejected, and then it making its journey across space to reach us here on the Earth. So we can make predictions, and there are now in place solar weather forecasting missions which can see these sorts of changes, and you can do various things, like, for example, move satellites down into lower Earth orbits temporarily, and this means that they're relatively protected, because as you move them down, they're within a denser magnetic field from the Earth. Also, there are wisps of the atmosphere in some places which can help as well, and so there are various things that you can do to mitigate, but it is still a major risk factor. And so we think as we rely more and more on these technologies, they're going to make a bigger and bigger impact on our lives if we don't take steps to predict them or defend against them.
So a couple of questions have come through. Thanks for that, Chris. A couple of questions have come through regarding our evolution. The one asks, are we really related to Neanderthals?
Well, we are related in the same way that we're related to other early hominin species. For instance, if you wind the clock back, you'll find that we share genes, or we have an ancestor which is Homo erectus, for example, and upstream of Homo erectus are all these Australopithecines. And South Africa is very famous for having a very rich record of the existence of these organisms. But what's beginning to emerge is that where people previously thought that evolution was this linear thing, where one thing came along and there were these organisms for a while, and then they just disappeared and some new ones were stemmed from those, and there was this sort of linear progression. What we now realise from the fossil record is probably that there's this very rich tapestry. Nature's doing lots and lots of experiments all at once, and it's almost like hair being plaited or braided, where you end up with lots of different parallel strands of evolution going on all at once. So as a result, you select from that the ones that's going to be most successful. So in some respects, if we wind the clock back far enough, yes, you're going to find a common ancestor. Chimpanzees and humans shared a common ancestor roughly 6 million years ago. So we're related to chimpanzees in that respect. And as you come forward in time, you will find that there are fewer steps between us and these other species. Neanderthals and humans diverged, hundreds of thousands of years ago and existed in parallel side by side until Neanderthals disappeared about 25,000 years ago, probably driven out of existence by anatomically modern humans, and possibly also interbreeding. We know that they shared genes because we interbred. So there were two things going on with it. We were definitely closely related to these things, and we had a common ancestor not too long before the two things parted.
Well, the other question about evolution comes from Trevor. He says, Chris, I heard you mention a while back that humans evolved from the sea. Is that why when we go into the water, we go into a euphoric state? I've heard that when we go into the water, our brains switch into another state, which is a calming, natural state of mind. Can you elaborate?
Well, I don't think we can peg the mammalian diving reflex on our oceanic origins, because when I said life came out of the sea, life on Earth was almost 100% guaranteed born in the ocean 4 billion years ago in the form of microorganisms. And in some places on Earth, you can still see these microorganisms in the form of stromatolites growing today. These are photosynthetic organisms which would have captured the various things from the atmosphere, including light, and use that to drive their biochemical processes. And they didn't do very much apart from just exist and build stromatolites for about 3 billion years. About 500 or 600 million years ago, then suddenly these single-celled organisms began to team up and make metazoal life, so multicellular life. But this is all still water-based. 450 million years ago-ish, we begin to see the first evidence of life invading the land. And so everything comes out of the water, plants, and then animals, everything else comes out of the water in the Devonian. So the reason that we actually have this mammalian diving reflex, this is slightly different. What this is that when you immerse a person, put a person's face in the water, their physiology changes, their blood pressure changes, their heart rate changes. It's called the mammalian diving reflex. It's certainly true that diving mammals like seals and whales, they have this physiology and they use it to control their oxygen consumption and metabolism when they're deep underwater. We probably have this ancestrally written into us because of being in utero. When we're a baby and growing inside our mothers, it probably has the same effect, and it might be that that's why we do this. But it's not because humans evolved in water. Humans didn't evolve in water. Humans evolved on land from other land-dwelling animals. But there are other animals that have taken this reflex and they use it actively in their adult lives. We probably have it there as a little bit of a throwback.
All right. It's said that we don't use the full capacity of our brains, and this listener would like to know what percentage we use daily and why not all of it. I think he's speaking about everyone but you.
Well, we do use all of our brain all the time, and the reason is that nature would not allow us to have such a metabolically hungry organ sitting there doing nothing, twiddling its neurological thumbs, because your brain is only about 2 and a bit % of your entire body weight, but it accounts for a fifth of all of the energy you burn at any moment in your whole body. So it's disproportionately energy hungry. And nature would not allow you to have evolved something that was burning off so much energy so wastefully, rather like certain politicians waste the resources of their country and then we get rid of them. It's sort of similar. Evolution would have selected out for a brain that was much more efficient. So you need all your brain, and you just have to look at someone who's had a brain injury and you'll see that they do have a deficit. They are not able to do everything that a person without that deficit would be able to do. Therefore, why do we get this idea that we only use a small fraction of our brain at a time? It's probably stemming from the fact that if you put someone in a brain scanner and you give them a job to do and you watch which bits of the brain are active, you can see that certain brain areas, when we do certain tasks, dramatically increase their activity. And this is because the brain is compartmentalized. There are different anatomical areas which are specialized for doing certain jobs. There are areas that decode vision. There are areas that encode movements. There are areas that encode thinking and mathematical reasoning and recognizing faces. So if you give someone a job to do or a task to do that's very centered on that particular role, then you will see a dramatic increase in the blood flow in that part of the brain and a dramatic increase in the neurological activity there. It doesn't mean that all the other things in the brain are doing nothing. It just means that in that area there's a relative augmentation temporarily, And I think that people have taken that to mean, oh, everything else doesn't do anything, therefore you're only using that bit of your brain. You're not. You're using all your brain all the time, but you've relatively augmented the bit that's doing the task that you're particularly focusing on at that moment a bit more over baseline, so it stands out as a bit more active.
All right, so here's another one. Isaac, this is definitely not for me, but he says, what causes shingles and how best to treat it? That's Isaac and Mitchell's Plain.
Hello, Isaac. Shingles is a manifestation of the same virus that causes chickenpox. This is called the varicella zoster virus. This is a member of the herpes virus family. The majority of people catch this virus when they're under the age of 5, and you catch it from someone who's either got chickenpox and is covered in spots, or you catch it from someone who's got shingles, and you can tell the two apart because chickenpox goes all over your body, whereas shingles is restricted usually, unless there's something wrong, to one strip of the body called a dermatome, and you get this eruption of this strip of very painful, itchy vesicles, little blisters, which suddenly appear, and you know it's going to happen because that patch of skin becomes tingly. Now, in people who have a dip in their immune response, they can periodically get shingles because your chickenpox virus, because it's a herpes virus, lives in you and in your nervous system for life. James Bond said, diamonds are forever, or is in the film Diamonds Are Forever. Well, herpes is for life. So if you get a herpes virus, you're going to have that living in you for the rest of your life. And in the case of chickenpox and herpes simplex viruses, which cause cold sores, they live in your nervous system, and the virus loiters there, and the immune system keeps it in check. But if you have a period where the immune system doesn't work so well for a while, and this could be stress, it could be malnutrition, it could be drinking too much alcohol, it could be that you have HIV, it could be organ transplantation and immunosuppression for that reason, a whole range of reasons. Every time your immune function dips, the virus gains the upper hand for a while, and then it erupts from one particular dermatome, this group of nerves that supply this strip of skin, produces these infectious vesicles. You can give someone chickenpox from that, so you have to be very careful who you go around and mix with when you've got shingles. And the way that we manage this is we usually give people acyclovir, which is a drug that stops herpes viruses. Acyclovir is a very good drug because it only gets activated in the cells that are actually growing virus, and it kills the virus off and stops it. In order to stop it happening, though, you can either sort out why you're getting shingles, so sort out your immune system, reduce the stress in your life, better nutrition, etc., or some people take acyclovir as a suppression dose regularly because they have to do that to protect them. The other thing you could do is there is now a vaccine, which is basically a weakened form of the chickenpox virus, which you give people an enormous dose of this vaccine, and it stimulates enough immune response so that they then top up their immune system so that they keep their own virus under control going forward. And that seems to work quite well as well.
Fantastic. Related to this, WhatsApp says, this person says their friend gets shingles when she gets stressed. And on the back of that, Blessing in Milnerton is asking, hi, Naked Scientist, which part of the brain is deeply affected when you're stressed? And smoking weed, is it a solution to stress relief?
Well, first of all, which bits of the brain are concerned with stress? The answer to that is that you have in your brain two regions, one on either side, in your temporal lobe called the amygdala. And this is about the size of an almond, so it's a small cluster of nerve cells in this region, and this is your brain's fear centre. And when the nerve cells there are activated, people describe feeling fear or anxiety. And if you put people in a brain scanner and show them pictures that might unsettle them or stress them or make them worried about something, this is the area on each side of the brain in the temporal lobe. So if you put your finger just in front of your ear on each side of your head, you're pointing roughly at where your amygdala is. That region is concerned with fear and stress, and also the condition post-traumatic stress disorder, PTSD. People who have a very harrowing, stressful experience, for instance, soldiers who go to war, often develop this, and there seems to be overactivity in the circuits through the amygdala and memory circuits. In terms of why we get stressed, well, stress is in some respects, in a small amount, good for us because it's motivating. But where it becomes toxic is when you lose control. Where you feel that you can't do anything to stop whatever the condition is that's making you feel stressed. You feel at a loss to control your own destiny. And this chronic stress is what leads to people becoming unwell. I wouldn't advocate anyone take cannabis for this sort of situation, because what you're basically doing with that is possibly putting a sticking plaster over a wound. It doesn't make the wound go away, it just makes it less noticeable. What you need to do is to ask, well, why are you stressed in the first place? What's causing this? Is there a way to change what's going on in your life so that the provoking factors are reduced? And then actually you will feel better, rather than just paste over the cracks, which basically just means that you're covering up the problem and it still remains there. You're just ignoring it for a bit longer, which means it probably in the long run is going to get worse, not better.
Indeed. So many more questions coming through. I wish we had a little bit more time. Chris Smith, the naked scientist, thank you so much.
It's a pleasure.
For
Thank
joining
you.
us this morning and enlightening us. These are fantastic answers.